So everyone, that's okay.
Yes.
Before we move ahead, any questions or queries from the last session?
Well, I don't think so, but did we get a chance to review that chain replication?
Oh yeah, that was.
I read that part. So it says that it works like a master leader follower, but in nodes, in pairs, and there's a subsequent linkage between the parent to parent. So there are two ways it's like connected. Rather than a single leader and multiple followers, it forms a chain.
Okay.
So chances of, that follower going down will not impact all the followers, or a leader going down will not impact all the leaders because the leader is attached to another leader, and only one follower is attached to one leader. It's a chain system. But again, needed more reading. Even I didn't get a chance.
Okay.
Yeah.
But so you mean to say all the nodes, whether it is a follower or leader, they are connected in a chain?
From what I read, the initial part, it was the leaders are connected to one after the other, and every leader has a follower node attached to it.
Oh, okay. Okay, so then there is a lot of replication, isn't it?
Yeah, I guess.
Okay.
But then that's very initial area which I read. It seems that they had eventually changed the structure also for that. Shall we look it up right now? If we can.
Can you repeat the question? Actually, I have some idea about the chain replication.
Hey, Banish.
Hey.
We were actually exploring what was chain replication, because last time when we were reading about the leader and follower, there was this note given over here that that new kind of replications are there. One of them is the chain replication, which is a variation of synchronous replication that has successfully implemented in few systems.
Yep.
Example is Azure. So I mean, for a leader follower, this is what we know today, right? This is how it looks. But the chain replication is something we were trying to understand how it works.
Oh, okay. Yeah. So chain replication, actually, let's consider three nodes, right? It's set up like head. So there is a head and there is a tail. Right. Then in the middle, you can have multiple layers, right? Multiple servers. So always the writes go to the head and the reads are going to the tail. So actually, the client's request to a write is only acknowledged by the tail. That means actually it's replicated till the end. That is a synchronous replication. And also it supports linearizability, right? So whenever a client writes something to the head, sends a request to the head to write, and so the acknowledgement will only be sent by the tail. That means actually it replicated through all the whole chain, right? So when the client again tries to read the same thing he wrote, he goes to the tail actually, right? Tail already has that information. That means actually it's linearizable.
Mm-hmm.
Am I making sense or?
Yeah.
Okay.
So only one thing is, go ahead, Shajan.
No, I'm saying if the chain breaks, like let's say there could be disconnection, right?
So there are three possibilities, right? Head breaking, middle layer breaking, and the tail breaking, right? Head and the tail breaking is pretty straightforward. So what chain replication doing is actually, so it is taking the logic of who is the head and who is the tail. That is controlled by the config mechanism. Normally it's controlled by a zookeeper or some system like that runs a consensus protocol. So the zookeeper looks actually, okay, that head crashed. So what it does is actually it knows actually how many servers are in that chain. So it will ask the next person in that chain to take over as the head, right? So so the only caveat is actually, let's say there's a request that came into the head, right? That was never replicated to the rest of the chains. So that write is lost.
Okay.
So it's not really lost actually. We never acknowledge that that request to the client, right? Client see a timeout. So basically,
So basically what you're trying to tell us, if I'm understanding it right, The replication is first, the write happens on the first head, then the
Yeah.
head replicates to the tail, right? And
No.
then the head would replicate it to the subsequent head.
No. So there is only one head and one tail in a chain. You can have multiple heads and tails, but actually for a system, right? Let's say you are talking about one shard. One shard will have actually one chain. There is a head, there is a multiple middle servers, and the tail. So head get the request. It writes to its own database in its own tables. Then it forwards a request to the next person in the chain. So the acknowledgement will be only sent back by the last person in the chain. That is the tail. Okay. So now we talk about the head failing, right? Now the tail failing. Tail failing is actually so basically that is pretty straightforward, right? The one person above the tail already has everything what tail knows.
Yep.
That is pretty straightforward. Then the middle layer failing. Middle layer failing is it's slightly complex, because then the person above the middle layer, the crash server has to tell the one below the crash server, okay, these are the updates you have to replicate. Okay, then actually it can work. Actually, there is one more case actually. So you may need to add one more server, right? Maybe at the very end. Add it to the chain. So you normally add the new server at the tail only, because that is the easiest place to add. Actually, you can read about that. Actually, if I start to explain, there are a lot of things to that.
Yeah. So this is what I had looked last time.
Exactly.
Chain replication. So when the write happens, it happens on this head, right?
Yeah. So head will write to its local storage, then forward the request to the next person in the chain.
Okay. So basically, it will first do it to its tail, right? It has to push that. It will have to replicate it to its tail also, right?
Yeah, it will write to its table. Yeah. It's not replication. Think actually both are same actually.
Okay.
Yeah, it's no leader follower like that kind
Okay.
of.
Could be log also, right? It could be log
exactly.
also. Let's
okay, got it. So this is basically in this linear fashion where it's storing it.
Exactly.
Till it goes to the large nodes.
Yeah. So why actually this is the most common approach if you look in industry, right? So you have a data plane and a control plane. Control plane is actually controlled by the zookeeper. Zookeeper decides who is the head, who is the tail, right? And zookeeper will tell the node, okay, you are going to be the leader, the head for this shard. So then zookeeper only needs very few servers, maybe 3 or 4 servers to keep that information. And this is actually the replication side of it, right? Replication, actually, there is no logic in the replication. But if you compare this with Raft or any other consensus protocol, right, then every node has to run the consensus protocol, right? Here, the nodes are very dumb. They only replicate whatever they get it, they write to the database and they forward it. But actually, zookeeper is the guy who is actually taking care of all the logic behind who owns what. So this is mostly a common approach in industry actually, except the Raft. Spanner does the opposite of that. Spanner does actually the Raft style of replication.
Even in SDFS also it happens, right? Master is there and then...
Yeah, exactly. Same. Actually, SDFS follows the same approach, right? There is a, let's say GFS, right? I have more...
GFS, yes.
Yeah. GFS, there is a master, right? That guy decides actually who owns the primary of that chunk, right? Then that primary is responsible to forward it to the other people in other servers, right? So that is also following this approach.
So you mean to say GFS follows chain replication?
Yeah, kind of. Actually, you can think about that. But actually, in GFS, the primary, the controller node is a single point of failure, right? Because if you apply the regular chain replication, then that controller node will have actually redundancy. So in GFS, I think they don't have it.
Okay.
So from intermediate nodes also it can be read, right?
No. No, right? So we only acknowledge from the tail, right? So let's say if people start reading from the intermediate layer, that then you'll see data inconsistency, right?
Then
So
what is the keeping of that intermediate node? So
what
much
is that?
why to unnecessary? What is the use of keeping such intermediate nodes?
Replicated, actually, it's fault tolerance. Let's say the tail fails or head fails, that guy will be the one in the middle, right? Will become the next head or next tail.
Yeah.
But that can be even circle also I can put, right? I don't. What is the significance of putting it in a like?
If you circle, if you make head and tail touch, right? Then actually, so the data will go into a circle, right? Infinite loop.
No, like head will be considered as master and tail will be as the follower. Why so many? I mean,
no,
I don't
then
get this chain we are using. Huh?
Okay, yeah. So let's say if you have that follower and the what do you call it, the master
Leader.
and the follower, right? Leader and the follower, then everybody has to know actually a consensus protocol.
Yeah.
Right here, actually, nodes doesn't know anything about consensus.
Yeah, so they are actually going away from that, right?
Yeah, what you're showing is the below one is actually consistent hashing, actually the ring.
Yeah. So I think it started. Yeah. So in this, when I'm looking at this thing, the way it's explained it starts with a very fundamental, structure of that chain replication. Then it goes about, sharing other ways. Like there's this appropriation queries crack. So here it is following a different approach. It seems that the read is happening intermittently. Write goes node by node till the very end.
So here he read is also from the intermediate nodes.
So the approach is different because they call it as the approach.
This is a different paper actually, crack.
So how this chain replication actually come fit with this hybrid replication where we do have some sync replicas and some async. It looks like here that request will hop all the nodes in that chain.
Yeah, this is sync actually. I don't know whether how they.
So looks to me that there will be more latency here.
So think about this, right? So here. The complexity of the system is actually what they consider here, right? Let's say if you are running a Raft protocol, right? In Raft, actually, all the reads and writes has to go to the master, right? So the master is overloaded here. If you look here, right, the writes goes to the head, reads goes to the tail. So you split the load of the master here. That is one way to look at it, right? So that is one way. The second way to look at it is, let's say you have 3 shards or 4 shards, right? In one particular setup, let's say the head right now you're showing in the screen, that is the head for the shard 1. So for the next shard, I will make the tail in this picture as the head, right? And for the third shard, the one guy in the middle will be my head and another guy will be my tail. So you can have multiple configurations with the same service.
No, but think like tree-like structure. What is problem in that, right? Latency will be reduced, don't you think? Because every follower will be directly contacting with the master, right?
So let's take, as Shashank said that, let's take one write request. So it always hit the write and go through all these middle nodes and then reach the tail, and then tail will reply. So let's say if we do have these 4 nodes in that chain, so that means one request will hop to these 4 servers.
Yes.
First, initially it will land at the head, then go to the next and go to the next. Okay. So which means that we do have we replicated this data at 4 nodes.
Yes.
Synchronously, because right.
Yeah.
But in that case, if one of the node is failed.
Yeah, one of the let's say one of the node, maybe the complicated part is one in the middle failed.
Okay, let's say third node is failed.
Yeah.
It's not reachable. So now the second node will system will introduce the next node here, or what?
No. Actually, system doesn't know anything about introducing anything, right? That is the data, the control plane. Control plane is controlled by the zookeeper. Zookeeper detects that actually, so the third guy in this chain is failed. Zookeeper will ask actually, okay, the second guy in the chain actually, can you forward all your commits to tail?
Okay, so second guy will. Okay, so you are saying that every time when request hit the node, it communicate with the controller and get the information about where I should send this request next.
No, the other way around, right? So when controller took over a chain, right, it will tell actually what's your position for each server. If anything changes, controller will come back and tell you. You don't need to contact every time the controller. The data is flowing from the other direction. So
how the head know that where I should forward this request?
So actually when this chain is formed, right, the zookeeper will contact the head and send a message to head saying actually you are the head. Your next person in the chain is the next guy.
Okay. So you're saying that the controller is controller push that information to these nodes.
Exactly. That's why they are calling actually this is why this is famous, because they are controlling the data plane and the control plane, right? If you look at Raft, they are both together. Every node runs the Raft protocol. That means actually control and the data sits in every layer.
Mm-hmm.
So because every node should know actually how to respond to a leader's request to a Raft message. And every person has to involve in the voting process, everything, right, in the Raft.
Mm-hmm.
Here actually it's the chain is whatever chain is doing, they are dumb of anything else, right? They only know actually get a request, write to database, forward it. Somebody comes and tells me do something, it will do something. That somebody is zookeeper.
Mm-hmm. So the dependency is on the controller.
Yeah. So now the single point of failure is the controller. You apply any consensus protocol, but actually you only need 2 or 3 servers, because controller only stores the config information, right? So it doesn't need a lot of servers mostly it will fit in one server's memory. So it will be able to replicate it across 3 machines, and one failure the controller can still run.
Okay, but see, if one of the node fails, you say that the previous node will communicate to the tail or whatever the way it was. But when it has failed, this guy still thinks that it has to send to the previous one will always think it is going to send to the next one till zookeeper comes and tells it. So during that period of transition, will there be issues?
There will, right? Actually, so the clients will see timeout. Right, actually the writes, but the system is always consistent. That's the key, right? So there is no half-baked information here. Actually, only tail will acknowledge the client that actually we accepted your right. So here actually the importance is given to linearizability. Actually, the system will always be consistent. But if you look at Raft, the master has to ask actually all the majority of the followers actually, do you update this data, or can I respond to this the read request, right? Actually he has to collect information from the quorum and compare and actually then send a response. Here tail knows actually if I have the data, that is the consistent data. I don't need to ask anybody else.
True.
Okay. So you mean to say for strong consistency, this is the best way to do?
Yeah, this is one way to achieve it.
Okay.
But quorum works in leaderless, right? Not in master follower architecture, right?
No, quorum read, it depends, right? Actually, so if you are using the leader based approach, then everything goes to the leader. Leader will be responsible to give you an answer. Let's say if you are using leaderless replication, then you have to read it from the quorum and you have to decide which is the latest value, and maybe you need to do a read repair or something like that if you see any.
High watermark, what you say, right?
Exactly.
Okay.
So at least in Azure, now Benish is referring to as data plane and control plane, right? So when client writes to the to the head and it forwards the writes. If it encounters similar failures, it it contacts the, I mean, here he was referring to zookeeper or something. There's a partition manager kind of thing. So they that is, I mean, the control plane forms another chain, so that I mean, the links may be broken, or it may take some time for the network partitions to recover, right? So and some of the storages might be exposed to the client. I mean, if it is Azure storage or something like that, we cannot wait for the broken link to uh, to get into a proper state as such. So that partition manager takes care of creating another chain like this, and asks it to commit to that other chain instead of waiting for it.
Oh, so there will be multiple chains running.
Yeah.
Oh.
That's more interesting. Yeah.
Yeah, it's more complex.
Can show you one. I can show you the diagram.
And those chain will be connected to other chain, or parallelly it would be running, like first chain then followed by next chain. There will be any connection or what? Sync, like all those chains should be
No,
sync.
actually chains are small set of nodes itself. 2-3 nodes
Cluster.
itself.
Okay.
Yeah, cluster kind of. 1 minute.
Uday, you're sharing your screen, right?
Yeah, 1 minute. I'm opening it. You guys can see, right?
Yeah.
Yeah. So this is the Azure storage kind of thing. So the partition, I mean, the control plane or the partition layer tracks how the chains are there, and whether there are any failures or something like that as well. If it encounters any failure, this creates another set of chain and starts committing it to that chain.
Okay.
Yeah, that's for the fault tolerance, right? Yeah, that's correct.
Yeah, fault tolerance.
But it will create only when there is a failure. So there won't be anything in parallel. Right?
There's one more thing. I mean, so the thing here is, I mean, if you say you have created one chain, there's a fixed amount of storage involved, right? I mean, you cannot go beyond a certain limit, right? I mean, the health and the storage you also need to take care of. So the control plane also tracks this kind of metrics and starts creating another chain whenever these are kind of sufficiently full.
Okay.
Or
So there is a lot of intelligence built in that. Okay.
yeah.
It's complex. Yeah, sure.
Actually, if you read that paper, that should be fairly straightforward.
Yeah. Yep. So thanks, Banish, Uday, Praveen. Yeah. Uday sir, let's move.
Yep. Okay. Cool. So, what conversation on the chain replication? Right. So now we are moving ahead, setting up new followers. So in case anybody wants to take a lead, you can just let me know. I can pass the baton. All right. So from time to time, you need to set up new followers, perhaps to increase the number of replicas or to replace the fail nodes. How do you ensure that the new follower has an accurate copy of the leader's data? Simply copying data files from one node to another is typically not sufficient. Clients are constantly writing to the database and the data is always in a flux. So a standard file copy would see different parts of the database at different points in time. The result might not make any sense. You could make the files on disk consistent by locking the database, making it unavailable for further writes, but that would go against our goal of high availability. Fortunately, setting up a follower can usually be done without downtime. Conceptually, the process looks like this. Okay. So we are looking at the steps of how the follower comes into picture. Take a consistent snapshot of the leader's database at some point in the time, if possible, without taking a lock on the entire database. Most databases have this feature, as it is also required for backups. In some cases, third-party tools are needed, such as backup pex for MySQL. Copy the snapshot to the new follower node. The follower node connects to the leader and requests all the data changes that have happened since the snapshot was taken. This requires that the snapshot is associated with an exact position in the leader's replication log. The important point here is this requires that the snapshot is associated with an exact position within the leader's replication log. That position has various names. For example, in Postgres, it is called as the log sequence number, and in MySQL, it is called as the bin log coordinates.
So that number is timestamp or what? Log sequence number, or like log is append only file. So
my understanding, it's a monotonically increasing number actually.
But there has to be limit to even monotonically increasing, right? You can't go beyond the certain 2 raised to the power 31 minus 8.
Yeah,
right?
but actually you can reuse the numbers after some time, right? Actually, because probably 2 days of replication you will have be lagging, right? I'm just
correct. So no, but like let's say billions of users where there are. I mean, if the QP per day, what do you say? QPS only, right? Queries per se. If that is very high, right? Then won't that number even get exhausted?
Yeah, probably. Yeah, we need to maybe research about that.
Like Twitter uses Snowflake for that, I think.
Oh yeah, I think Twitter Snowflake is also increasing, monotonically increasing, right? So I think can be used.
Yeah, could be. But some other things also they introduce, I think, characters, or I'm not sure.
But see, this is the followers, these are the nodes. So this is nothing to do with the users, isn't it?
No, but appending it to the log, right?
Yeah, but he's going to
Like,
not append to each and every user request as such. It's going to be a bulk update. Like a snapshot, no? So snapshot of a certain time. It won't happen every second.
He's referring to the part after the snapshot is taken.
Exactly.
Yeah, he's referring to those changes, how to capture those
Yeah,
changes.
but for that, we don't need a log sequence number, isn't it? So that is just directly going to the leader and taking all the requests.
But then how will it know that were the new changes or not? The snapshot was taken, right?
Yeah, so snapshot, whatever we take, that is what is related to sequence number, isn't it?
No,
other thing, right? Like every time once you, before putting it to the DB, you put it into log, right? So it's append only log, right? And
so no, I was saying actually there are two things, right? Actually, so when you take the snapshot, you tell actually send me everything till 10 o'clock, right? So I'm started copying everything till 10 o'clock, but actually it will take half an hour to copy. From 10 to 10:30, there are new requests coming. That is not part of this snapshot, right? So master is actually tagging with a log sequence number to all the requests that came in from 10 to 10:30.
Oh, so the log sequence number is after the snapshots.
Basically, everything, even within the snapshot, actually you can see the log sequence number, because everything is tagged with a sequence number. Right, but actually in this case we are mostly interested about anything that happened after 10 o'clock, because everything before that is actually already in the snapshot. I'm not worried actually, so I just need to know everything after. So let's say the 10 o'clock the snapshot was taken with the log sequence number of 100. So then I will, after I copied everything, I will go back to the master and ask actually send me everything from 101 log sequence number.
Yeah. More like it will just check, I have got the latest as 100. Does my master has 100? He will say, oh, it's not 100. It's like 110 or 150. That means it will understand that, okay, 50 new changes have been recorded and that needs to be taken. So it will start reading it. And I think so that position, right, where the difference of 50 is coming, that's where this, they have termed it as log sequence number or bin log coordinates.
Okay, yeah, thanks.
Alrighty, so that's that. And when the follower has processed the backlog of the data changes since the snapshot, we say it has caught up. It can now continue to process the data changes from the leader as they happen. So once that work is completed, they call it as it's caught up. Practical steps of setting up a follower vary significantly by database. In some systems, the process is fully automated, whereas in others, it can be a somewhat arcane multi-step workflow that needs to be manually performed by an administrator. Cool. I hope everybody is getting it. Any questions or queries, please ask. Okay.
Yep.
Moving ahead. Handling node outages. Any node in the system can go down, perhaps unexpectedly due to a fault, but just as likely due to planned maintenance. For example, rebooting a machine to install a kernel security patch. Being able to reboot individual nodes without downtime is a big advantage for operations and maintenance, right? Being able to reboot individual nodes without downtime, right? It's a big advantage for operations and maintenance. Thus, our goal is to keep the system as a whole running despite the individual node failures and to keep the impact of the node outage as small as possible. That's the intent. And how do we achieve high availability with this leader-based replication?
But there will be downtime, right? While copying the data, like if node fails, right, from master, if you copy the data or take the snapshot, there will be downtime at that time, no?
Right, they're trying to minimize it, most likely.
No, it will be highly available, maybe not consistent, but downtime, I don't think it will have.
Okay, it will accept from the client, but read might not be consistent, right?
Yeah, this is what I'm thinking.
Zero downtime. Okay.
Yeah, I think it has to start the copying of that snapshot again, right? Or is it going to be?
I mean, I think its availability is what focuses here, so that the reads and writes can keep on happening. But as Divya mentioned, that the reads might not be consistent. Maybe there's one node which is still coming up, doesn't have the latest data. So maybe that's the only caveat here.
Sure.
Okay. So the first approach, follower failure, catch-up recovery. On its local disk, each follower keeps a log of the data changes it has received from the leader. If a follower crashes and is restarted, or if the network between the leader and the follower is temporarily interrupted, the follower can recover quite easily from its log. It's known as the last transaction that was processed before the fault occurred. Thus, the follower can connect to the leader and request all the data changes that occurred during the time when the follower was disconnected. When it has applied these changes, it has caught up to the leader and continue receiving a stream of data changes as before. So, okay, I hope everybody's clear with this. It basically means that it's keeping a track on the basis of a log, and whenever they recover, they know the last transaction that was processed before the fault happened, and they move beyond that. That is follower failure, catch-up recovery. Okay. Next one is leader failure, failover. Someone say something? Okay.
Nope.
Okay. So now we're talking about, so this is follower failure. Now we're talking about leader failure. Handling a failure of the leader is trickier. One of the followers needs to be promoted to the new leader. Clients need to be reconfigured to send their rights to the new leader, and other followers need to start consuming data changes from the new leader. This process is called as the failover. Failover can happen manually. An administrator is notified that the leader has failed and takes the necessary steps to make a new leader, or automatically. An automatic failover process usually consists of the following steps. First, determining that the leader has failed. There are many things that could potentially go wrong: crashes, power outages, network issues, and more. There is no foolproof way of detecting what has gone wrong. So most systems simply use a timeout. Nodes frequently bounce messages back and forth between each other. And if a node doesn't respond for some period of time, let's say 30 seconds, it is assumed to be dead. If the leader is deliberately taken down for planned maintenance, this does not apply. Okay, so the first is determining the failure, and it is done via the bouncing of the messages back and forth between the nodes. Next is choosing the leader. This could be done through an election process where the leader is chosen by a majority of the remaining replicas, or a new leader could be appointed by a previously elected controller node. There is the entity called as controller node. The best candidate for leadership is usually the replica with the most up-to-date data changes from the old leader to minimize any data loss. Getting all the nodes to agree on the new leader is a consensus problem, which is discussed later on. Okay.
So,
here we are,
go ahead. Yeah. No, what I'm saying.
Go ahead. Yeah. I was just summarizing.
Like gossip protocol doesn't work here, right? I mean, I'm saying gossip protocol doesn't work here to detect which node has failed. That will work only leaderless, right? Like everybody sending message to everybody, right? To pass it current state.
Yeah, at least that is what I know about gossip used in leaderless. But you never know, there might be in hybrid ways to do it. But here, what I see in the first point, when they are saying, like how to determine the leader has failed, and they're saying there will be a time period of 30 seconds. So is it possible that the leader is still failed during that 30 seconds and no one knows about it?
Beyond 30 seconds, I guess.
Okay, so it at least takes 30 seconds to come to a conclusion saying the leader has failed.
Yeah, maybe the assumption here is that it take 30 seconds for the one transition of message from one node to another. Beyond that, it will feel that okay, now it's like normally we have timeouts, right?
Yeah. So is it like we are without a leader for almost 30 seconds? Maybe a possibility, isn't it?
Yeah.
Fair chance.
Okay.
If there is no, but that's an arbitrary number, right? Or it's like experimental.
It's arbitrary. Maybe it's say 30 seconds, right?
Yeah. So whatever that number may be, but still for that much of time, you might get a lot of requests, and then leader might not be handling them. Okay.
Correct. That will be downtime. Yeah, I think Divya was mentioning there won't be, right? I mean, that was some other case, but that will become ideal system, zero downtime, right?
Yeah, but actually, by the time system, so it's everybody's perspective, right? So leader is still think. Let's say a leader is only partitioned out of the network, right? Rest of the guys can talk each other. Leader still thinks actually he is the leader. He tries to contact everybody. Leader thinks actually everybody else is down, right? The other guys think actually leader is down. So that I think 30 seconds is the time actually. Then by the time the next leader election should be started. So because
for that much period of time, leader is down, right?
Exactly.
I mean, leader is not able to communicate, right?
Yeah, because so if leader, because the client may be able to connect to the leader, but leader won't be able to talk to its peers. So it cannot write, it cannot accept any writes.
Correct. Right? Yeah, the writes would be failing here. Whereas the reads might keep on happening, but the writes will time out in this case.
No, in leader based actually reads will also go to the leader, right? In a leaderless only actually.
In leader, in master, I mean in leader, the reads goes to the follower, not the master, right? Only the writes is accepted by the leader.
No, then there's a problem, right? Actually, I have 5 machines, right? And let's say I have 3 machines, right? I need the quorum of 2 to write, right?
But in leader, there is no quorum, I think.
What is that?
In leader, there is no quorum.
Yeah, leader is part of the quorum actually. So let's say it's if there are 3 nodes, I can have 2 read and 2 write quorum, right? So leader is part actually.
I think the sync replica is like that, right? So,
but there is, I think quorum only works in your leaderless kind of thing, right? Where you have 3 for read, 2 for write, r plus w greater than n, right? That equation.
But in Raft, yeah, Raft is a leader based, right?
Raft is leader based, yes.
Yeah, if I remember it correctly, it needs the majority quorum to accept a write. Otherwise, actually, so the data won't be, because at least you need one guy from in the read and the write replica to be common, right? Otherwise, you will have the stale data.
so like a sync replicas, you know, so you maintain some sync replicas. So that may be a sort of quorum, but we are used to have that quorum term to be for the leaderless.
Leaderless, correct? Yeah.
Yeah, but you can have a group of followers saying, okay, these are the sync replicas, which I would also consider. You know, so they are almost in close to the leader. So had it been,
or they will have some high watermark kind of thing, right? Where every follower says, okay, I have data up to this, right? That means that is also part of one such way to tell the consistent information, right?
So the high watermark is considered only when we want to compare between those followers or whatever may be the replicas what we have, and we find which is the replica. All of them have the common data to the maximum extent.
Correct. That means everybody is consistent, right? That means everybody is consistent in that one, right?
Yeah, I don't know.
No, so now there is a chance. No, I was saying actually there is a chance that actually if you are using quorum, and if it is not absolute quorum, then there is a chance that one of the replica may be lagging, right? So if I have,
that is for lagging itself, we use this high watermark, right? So that all of them should be in at the. I mean, they will report to the leader, hey, that like I up to this. I mean, what this is the mark till which I'm having the data, right? If any one of them is behind that, then other follower it or the master will try to make it to that level. No.
Yeah, I agree. Yeah.
Yes, go ahead, Mutsar. You were trying to say something.
Nothing. I was just looking it up. I mean, the very first area of leader master, the reads are kind of happening all across the followers as well as the reader.
Yeah, in some cases you can have read and write from the leaders. In some cases you can have reads from the followers also. It depends on how you are setting up the system. But usually having it from the master is always good.
So I mean, that depends on your system requirement. So if your system say that, okay, we want to support that read your own writes, or so that, I mean, if a client writes something and they want to read their data back, and let's say if instead of redirecting to the leader, it goes to one of the replica which was not updated yet. So in that way, the client will not see its own data. So if you are supporting that kind of consistency, okay, we want to support that read your own writes. So in that way, you can go and read only from leader.
Exactly. Yeah.
So another is that, I mean, as we discussed the other day, that okay, what is the reason why we want these replicas? If my read load is way high that one system cannot afford that or cannot support that, then definitely we need to actually redirect to these replicas. And yes, there is a trade. We are okay with some inconsistency here.
Okay. Yeah. So that the eventual consistency still, but your read load at least
high availability.
Yeah.
High availability resides. I think in sharding also the same approach would be getting used, right? That in the sharded partitions, the read can be happening all across the sharded partitions, but it's highly available. But the replication might be at its own pace.
So there is one thing to consider, right? Actually, why we are introducing a leader because we want to make a total order of the request, right? So if you don't care about the total order, we don't need the leader, because we need to serialize the requests coming in, and we need to support linearizability. That is why we need the leader, right? So if you are allowing any request to go to a slave which is not updated, right, follower, then actually we are breaking linearizability, right? So I don't think any of the leader based systems will allow you to write read from the follower, because that is gonna break the linearizability, right? So if
It's about
Can you
reading.
elaborate?
Oh, it's about reading. So you're saying that you're thinking that most of the system will not allow that, or
yeah,
that's not
so,
the valid use case.
because because the leader based systems are designed mostly for the linearizability. That's my understanding, actually. You guys can correct me. So if I am okay with eventual consistency, I don't care about the leader. Actually, I can do the leaderless. So I know actually my system is eventually consistent, so I can see data consistency. But if I am guaranteeing my clients that actually I support linearizability, then I can never allow my clients to see any stale data, right? So that means actually I support linearizability, and my reads and writes should be forwarded to my leader.
But then asynchronous, I will not follow that linearizability, right? In that case, it would be the use case which you're referring to would primarily apply on the synchronous part. Whereas if it's an asynchronous system, it would not really confirm or guarantee that it will always be there on the follower. It will be a instant hit read.
Exactly.
Acknowledgement is only at the leader level, not at the follower level. Yeah.
Praveen just mentioned, right, read your own write consistency. That is where the linearizability is main, right? I write something because I posted something on my Facebook page, right? So as soon as I posted it, I go to my home timeline and see whether the post is still there, right? That is basically the read your write consistency. If let's say our system is allowing clients to read from the one of the followers, right, and the follower is taking some time to replicate. Now, when I go to my home timeline, I don't see my post. That will confuse me, right? So that is why they want actually linearizability for some systems. But if you look at the Amazon's cart, actually, I don't care, right? Actually, I add an item, maybe it disappear, maybe after some time it will come up again. So that is their system, right? So for them, Dynamo system is leaderless. For Facebook type systems, they are emphasizing on linearizability / read your own writes. Linearizability is more stricter than read your writes. If you're having a system having linearizability, that means actually anybody, if I write something and you go to my home timeline, you should see my post. In read your write consistency, it is not guaranteed. I am only guaranteed to see my write. So you may be seeing my write maybe in after 10 seconds.
Yeah, that's fine for the social media applications, right?
Sorry.
And that's fine for that is eventual consistency, right? After 10 seconds, even if they read, that's fine for.
Exactly.
So this is the perfect scenario you just explained, that where you will support that read from your replicas. So if you post something, your read direct you should read from leader. But if I'm your follower and you posted something, it's okay if I see that after 10 seconds. So in that case, I don't need to read directly from leader. I am okay to read from one of the replica.
But what happens in those cases if the replicas are not exactly in sync, and if my write first goes to a very good replica, and after that again I try to read it, it goes to a worst replica. So then whatever I am viewing, even for social media, will be a confusing, right?
That's what I mentioned, that it's read your own rights.
So is it possible, say,
only for a follower? Suppose if I'm just reading someone else's timeline, okay.
Yeah. So if you go in that book, so author actually discussed that scenario as well. What you mentioned, that So going back in the time. So first you make a read request, it go to the one replica and you see the up-to-date data. Now you refresh your page or you make a request again. Now this time the request land up onto the different replica and that replica is running behind. So you will not see that up-to-date data now. So that is one issue in these leader-based system.
Okay.
Is this possible, say, for linearizability, right? It's kind of commitment that once it is written, whenever the read would be there, the same value would be given. At the same time, if we want SLAs or this whole process should be very quick. We in the process when the replication is in progress and something comes to follower side or things like that, we are considering those cases, right? But again, it's up to linearizability is when we commit on the snapshot version that what would be the returned, right? It's okay if we have multiple snapshots on those machines, but we are committing that this snapshot version would be referred whenever any read happens. So does it make sense? Or I was just, watching something on YouTube side, but on linearizability mainly. And that's where this concept was introduced there.
One more thing, what is the difference between linearizability and serializability? Both are one and the same or what?
No, linearizability, what my understanding is, serializability is just how we are transporting the data, right? It's not about the commitment of same version. That's what, like serialized and deserialized data, how we'll be passing it. And when it comes to linearizability, sorry, it's more about the version which we are committing to, or snapshot we are committing to. It's kind of overlaps with the strict consistency concept, but that's where
Okay. Yep.
What is the advantage of reading my own right? I mean, that I already know, correct? So I don't know why people.
No, but then you will confuse yourself if you write, and then if you are not able to read your own data, so you will try to write it again. So maybe something like that. So to avoid all those things, I think they do that, or maybe it won't be a good experience also for the user.
Yeah, it will be duplication of the submission.
Serializable, you talk about transactions. Linearizable, you talk about a system.
Right. Yeah. So
I mean, you say that the transaction is serializable and the system is serializable. Oh, sorry, linearizable.
Yeah. So what I understand more about the leader-based system is more towards linearizability, right? It's trying to. Okay. Okay. Yeah. No problem. Sure. Go ahead.
All right. Yeah. That's cool discussion, guys. Right. So we were just revisiting we were talking about failovers, leader failover particularly. And we were in the stages, determining the leader, choosing the new leader, right? Then wait for the next part. Next part is basically reconfiguring the system to use the new leader. Clients now need to send their write request to the new leader. This is as discussed on page 1.4. Okay, if the old leader comes back, it might still behave that it is the leader, not realizing that the other replicas have forced it to step down. The system needs to ensure that the old leader becomes a follower and recognizes the new leader. So important stuff being mentioned here is that the follower is pointing to the new leader, and in case the the old leader comes back up, it needs to go become as a follower. In case if it does, that's the key part mentioned here. So yep, that's that. Failover is fraught with things that can go wrong. If asynchronous replication is used, the new leader may not have received all the rights from the old leader before it failed. If the former leader rejoins the cluster after a new leader has been chosen, what would happen to those rights? The new leader may have received conflicting rights in the meantime. The most common situation is for the old leader's unreplicated rights to simply be discarded, which may violate the client's durability expectations. This is the easiest, just discard it, finish. Okay, that's one thing. Discarding rights is especially dangerous if the other storage systems outside of the database needs to be coordinated with the database contents. For example, in one incident at GitHub, an out-of-date MySQL follower was promoted to leader. The database used an auto-incrementing counter to assign the primary keys to the new rows, but because the new leader's counter lagged behind the old leaders, it reused some primary keys that were previously assigned by the old leader. These primary keys were also used in a Redis store. So the reuse of the primary keys resulted in an inconsistency between the MySQL and Redis, which caused some private data to be disclosed to the wrong users. That's sad. Okay. I hope everybody is getting this part right. That the promotion happened, but it seems the primary key assignment got messed up because the old leader and the new leader did not have the right counter. Yeah. In certain fault scenarios, it could happen that the two nodes both believe that they are the leader. Right? Both the nodes feel that they are the leader. Okay. In this situation, is called as split brain. Okay, and it is dangerous if both the leaders accept rights and there is no process for resolving conflicts. Data is likely to be lost or corrupted. As a safety catch, some systems have a mechanism to shut down one node if two leaders are detected. However, if this mechanism is not carefully designed, you can end up with both nodes being shut down. I mean, this is so humorous, if you think about it. Two leaders getting promoted and two leaders getting shut down for some
So
reason. Yeah.
Paxos resolve this issue, right? Split brain. Again, consensus algorithm, right? Like both the leaders will, two nodes will think that both of them are masters, right? They are not able to communicate.
They have that some versioning system, right?
Yeah.
Okay.
They agree to some common value, and based on that, they.
Yeah. The one which request is received from the greater number will always be accepted, and you will be informed.
Is that the election process?
Election.
Or, yeah. In this scenario, both are elected, but one was timed out and coming back. And then somehow there should be some intelligence to find out that there are two leaders and one should be shut down. Or is that the thing?
Yeah, right. So you mean to say that has to be done by a consensus algorithm, or maybe a coordinator, someone outside the system?
Yeah, there was something called as controller node. There is something called as controller node also, I think so. It's a third party thing.
Mm-hmm. Or when followers are getting through commands, they can also say that someone is not leader, or I'm not sure.
Mm-hmm.
Is that the possibility?
I mean, I don't remember exactly that, but something like what Santosh mentioned, right? The greater number used to get up. That is election process, or I don't recall that actually much.
There has to be some record somewhere where it would say that, okay, this is the leader, take this guy or use it from this.
Something like that, yeah. I think Sridhar is not here, right? He has only explained that. Okay, let's.
Yeah. So what is the right timeout before the leader is declared dead? A longer timeout means a longer time to recovery in the case where the leader fails. However, if the timeout is too short, there could be unnecessary failovers. For example, a temporary load spike could cause a node's response time to increase above the timeout. Or a network glitch could cause delayed packets. If the system is already struggling with high load or network problems, an unnecessary failover is likely to make the situation worse, not better. Okay. So interesting part where it says that what is the timeout? Can't be too long, it can't be too short. There is no easy solution to this problem. For this reason, some operations, the teams prefer to perform failovers manually, even if the software supports automatic failover. These issues, node failures, unreliable networks, trade-offs around replica consistency, durability, availability, and latency are in fact fundamental problems in the distributed systems. Later on, we will discuss them in greater depth. So this is the part where we are looking at for failure. Any questions so far, guys?
So there is no straightforward solution. Means there is no formula as such. So that is obvious because it's a very complex system. So, but based on your use case, and I think Praveen keeps on saying that. So what is your requirement, your use case, based on that, you have to select your best option. So you still will have problems for certain cases, but those will be minor and they will not be reflected for your system. So that is the way it should be designed.
No hard and fast rule, right?
Yeah.
Right. So whenever you come to, when you are designing a system or implementing it, so you need to find out what is the best option you can use. And still there won't be a very 100% solution. So you'll have to find some implementation based solutions also when you are designing your system.
Yeah, I think that makes sense.
Okay. Okay, so the next topic is about replication logs, where it talks about statement-based replication, write-ahead log shipping, and logical log replication. I think if we can take it tomorrow, and then move ahead from there.
Sure. I think we are almost on the time. Yeah.